Alright, so we'll start with number 5 here, which is a clock on a spaceship moving at the speed of 0.815 c, so 81.5% the speed of light, advances 13.2 seconds. How much time elapses for an observer at rest? Okay. So we want to start off with our y. Let's see. Which clock is going to have more time passed? The one on the ship or the one observing the ship moving? The observer. So, I'm going to start showing you understand that. More time passes for the observer. The observer. How about the faster the relative velocity, the greater difference in time. And then our biggie, the speed of light is constant in all frames of reference. Right? That's why all of this happens. That's our constant. Good? Similar? Okay. Excellent. So now the how. I'm going to grab, this is about time. I'm going to grab time. And since I'm dealing with different frames of reference, I better grab my Lorentz transformation. Right? I think that's all I need. Yep. So I always find it useful when I'm doing the how to keep in mind things like that gamma is always greater than 1, and therefore delta t is always greater than delta t naught, right? That's that logical step we went through when we were doing the example problems. And if I keep that in mind, I know right away that delta t is the one. They actually didn't say Earth, did they? This is the one from the observer, and this is the ship, right? So I know that delta t naught is the one given to me, 13.2 seconds. And my v, of course, I'm going to keep 0.815. I'm going to keep that in terms of the speed of light, because I find the math is just easier that way, right? Sometimes, actually, what you'll see is gamma, you'll see gamma written like this. Where they join the V and the C together. And so that sometimes makes it clear that the C's in the V and the C are going to cancel out. Right. So give it a try. See what you come up with. If you need my help with the math, I'll be glad to. I'm going to give it a try and see what I come up with. All right, number 4. Length of an object is moving with 0.91 c if its length at rest is 2 meters. So, I'm going to start off length, dimension in direction of travel, of motion. Contracts when moving. So they tell us what it is. Object. The object will be shorter when observed moving. And why does this happen? Why does this happen? Why does all this happen? The speed
the faster it moves,
of light
is
is constant. All frames of reference. All right, good. Lovely handwriting. So let's see, we're talking about length. Oh, we're going to need that Lorentz transformation. Might as well put that in, right?
how's it do tomorrow?
I think if you look, I said him due Wednesday. I would get him done, but. Yay?
Yeah.
Okay. So, how does L relate to L naught?
L is greater. Wait, no. L naught. Would it be less? I think it's getting smaller.
Well, remember gamma is always greater than 1. So if gamma is 2, how does L relate to L naught? L naught is always bigger. Try. 10 over 2 equals 5. Remember, if you're looking at relationships and you're like, I don't know, try throwing easy numbers in there. Just avoid the number 1 because that just doesn't tell you anything. But all right, so that means that L naught is from the object. Oops, that's an A, not an O. It means L naught is what the object measures, and this is what the observer measures. So that means L naught is our 2 meters, our V 0.91 C. All right, so go ahead, give it a try.
We're going on.
All right, so E-blocks right after lunch. Is that schedule there?
Yeah.
Oh. All right, moving on to number 3. We got this unstable isotope. How long does it take to decay when it moves at this? All right, so here's the Y. I copied in the Y from number 5 because they're the same. Yay!
Yes. Oh, wow.
And maybe I can even grab. Ooh, I
The
can't.
same two equations. It really be like that.
All right. So now, of course, we know that delta T is greater than delta T naught. So, do they tell us the name of this particle?
Unstable isotope.
Unstable isotope. Let's call it George. George.
I like the way
So this would be George, and this would be the observer. And so delta T naught is my time that's given, 21 seconds. And then my velocity is whatever is given, 0.75 c, 0%. But do notice they want my answer in 2 sig figs this time. So just, not that it's going to mark you wrong, you just wanted to kind of keep that in mind. So yeah, then it's just going from there. Someone was talking about number 7, and while I'm not sure if we have time to do 7, we could talk about it. It's the same as 5, wasn't that or 4 that we did with the lengths? But here they give you the 2 lengths, and they ask you to find the velocity in terms of c. This is where again I would think of solving for v over c rather than solving for v, because like if you've got the velocity is let's say that the velocity of something is 0.945 c. Well, if you solve for v over c, you get just that percentage, right? Divide both sides by c. This, a good way to think of that term is, that's the velocity in terms of the speed of light. So when you look at that Lorentz transformation, if you group it how we talked about before, think of that as v over c inside the parentheses. And just think of that as a single variable rather than 2 variables. Your life will be better. Okay?